Okay, so let's get started. So today we have Pedro Assis for the seminar. So Pedro is an assistant professor at Technical and also a researcher at LIB. He specializes in particle and astroparticle physics, mainly on detectors, instrumentation, and electronics. The main research interest is on the physics of cosmic rays and extensive air showers. And so within the Pierre Auger collaboration, Pedro has focused on precision measurements of extensive air showers, first by studying the response of fluorescence of the detectors, and now also with direct detection of secondary particles at the ground, which I think is more of what we're hearing about today. So, please, Pedro.
Okay, so thank you. So, in today's seminar, I will focus mainly on the detection of particles on the ground from cosmic rays. And so I will start by explaining a little bit what are cosmic rays. Cosmic rays were discovered like a radiation that comes, or rays or particles that comes from the cosmos, and hence its name. In fact, now it's assumed to be charged particles that come from the cosmos. It can be low energetic, mainly from the sun, and then you have all of these. Part of it comes from the galaxy, and part of it comes from yet unknown sources. They can be, well, you can include photons and neutrinos in cosmic rays, but they can be basically between protons and ions, and this is basically the main discussion at this point. So how do we detect them? Because we have 1 per square centimeter, 1 per square kilometer per century, and so since we don't want to wait centuries, we need to detect them indirectly, and we need to have a huge detector. We detect them indirectly because they interact in the atmosphere, in the top of the atmosphere, and they will produce a cascade of particles. And you can see, basically, you have some 3 sectors. So you have a part which is still hadronic, you have a part which is electromagnetic, and a part which is muonic, and these have different behaviors. The hadronic will basically feed this and this part. The electromagnetic, once you get to electromagnetic, it stays basically. So you have multiplication of electrons, gammas, and electrons. And you produce fluorescence in the atmosphere, and then they reach the ground, some of them. Muons will basically reach the ground. They won't interact, and they directly reach the ground, and they can come from the top part of the cascade. So our detector is something like this, is the Pierre Auger Observatory, which is a hybrid detector, where we have basically 2 detectors. The fluorescence detector, which provides a quasi-calorimetric measurement of the energy of the showers, and the water Cherenkov tank, or the surface detector, or simply the Cherenkov tank, or just the water tank. And so there are many names for it. You use these devices like this. The movie didn't kick in. Oh, not working, sorry. Okay, so this is an animation. You can later see it. And so the front of the shower, it propagates like a plane, like a disk of particles. And if you sample this disk, you can get information about the disk. The timing gives you information about the direction, and the number of particles that you sample in a certain area gives you the density of particles at that distance from the core, and then you can reconstruct the whole shower, the whole surface, and infer about the shower. Okay, where is this? This is in Argentina. You have here Rio de Janeiro and São Paulo. Here is Buenos Aires. Then you go to the left, and you reach almost the Andes, and it's here somewhere. It's in the Mendoza district, where you can get good wine and good olive oil. We have 1,600 detectors. Each of these is spaced by 1,500 meters. The covered area is 3,000 square kilometers, which is roughly 60 by 60 kilometers. The array has this shape, and it might not impress you, but hopefully this one will be more impressive. So this is the array. This is our detector. Here you have Lisbon, Setúbal, and Santarém, and you have each of these dots is one water tank. The other thing to notice is these 4 telescopes overlooking the array, and the central campus is here, meaning we live here, and if you want to go to the array, you start from here. You have a road like this, and the other parts are more difficult to assess it. So, the fluorescence detector will make a quasi-colorimetric measurement. So you have a UV telescope. This is the entrance. Here you have the mirror, and here you have the camera, which is 440 photomultipliers in here with light guides. The particles from the shower will ionize the nitrogen, and the nitrogen de-excitation emit UV light, and this is how you measure the energy. This is what you get on a low energetic and very nice event, because you have the low energy extension and the regular telescopes. The regular telescopes only see up to 30 degrees in the sky, and so you can only see larger showers. If you look at 1 pixel, what you get is this time trace where you don't have light, and when the disk of particles crosses in front of that specific pixel, you get the light and then it dies. Then you reconstruct it and you get what we call the light profile. Start of the shower, then the shower develops, it reaches a maximum, and then it dies, and then you can fit it, and from here you can extract the energy. For the surface detector, it's a bit more complicated, although it's a simple detector. So you have a tank full of water. Charged particles crossing it will do Cherenkov. Photons will interact and probably make a shower, and electrons also, and the charged particles will also do Cherenkov. And so you collect the light in 3 photomultipliers, and you get something like this. This is a display of one event. Here, the size of these circles represent the amount of signal that the station recorded, which is basically proportional to the number of particles that you had in the shower. And so you can see the shower is this size, more or less, and the impact point is the barycenter of it. And then you see these colors. It's the different timing of activation of the stations, and so you have it going from here to here. If you go to one station, you can see this time trace. So this is signal recorded, and typically these small peaks represent muons, so particles that cross the whole tank and give you a lot of signal. And this background, this more continuous background, represents typically electromagnetic part, where you have more particles, but they don't cross the whole tank. And so they are distributed in time, and it makes you a signal which is more constant. Okay. So just to show you a nice development by LIP, this is the 3D display. You might have seen it in the outreach sessions or in the master classes. It's the display which is commonly used in Auger. So this is a standard tool for the visualization of showers, and you can see here the footprint of the shower, and you can see this one gave light to 2 telescopes in here and in here, and so this is the reconstructed one, and then you reconstruct the parameters of the shower. Okay, results from Auger. you have a multitude of results, and just to look at some of the more important, you have a really high definition on the flux of cosmic rays. So this is the flux multiplied by e to the third. And so if you have a progression with e to the -3, this should be flat. And then you start seeing some structures that are still object of debate. This one is the famous suppression of the flux at the high energy, which at the beginning was thought to be GZK, but I'll get to it. The other thing that we saw is that we have a dipole which is not aligned with the center of the galaxy, indicating that most energetic cosmic rays come from out of the galaxy. Then we have limits on neutrinos and on photons, where we don't have photons and neutrinos, and this is excluding a lot of scenarios, top-down decays of strange particles, let's say it like that. And so this is excluding a lot of scenarios. And then we have, let's say, the hot topic, which is the mass composition evolution towards heavier elements, or simply the mass composition, where you would expect a simple scenario like proton or iron, because proton is very abundant and iron is the limit on the stars. And then you start finding that the proton fraction is decreasing, the helium fraction then rises, then you have the nitrogen, and you have very small iron at the highest energies. And unfortunately, in the suppression region, we don't have data which is significant. And so you can see the flux, it's very low, so the number of events is also very low. So, is it mass composition, or could it be something strange happening at the higher energies interactions on the development of the showers? To help with this, one parameter that we can look at, or one variable that we can look at, it's the number of muons and its fluctuations. And you find that these are the simulations basically for different primaries. And then you have here your data. And if you look at the mean, it's off. If you look at the fluctuations, it's not off. And this poses some strange scenarios that might indicate that you don't have a bad description of interactions at very high energies, which would impact on the fluctuations, but you have the description of what's happening more, and this is interactions at low energies. Auger is not a perfect experiment to measure the muon quantity, and you can see the error bars there. And so we need to increase the precision and to measure muons to disentangle scenarios. So we need more information here, hence the upgrade of AugerPrime. And the idea, if one would have to summarize it in only one topic, it would be this one: to install a scintillator on each water Cherenkov detector. It is a scintillator not segmented, so all this area is active and is installed on top of the water Cherenkov tank. Okay, so this is the, let's say, the main idea. Someone could kill me for saying this, but okay. The other things is UUB, so you need to upgrade the electronics to have better sampling of the signals, but also to support new detectors. And so this is just to show you that it's a complex job to redesign all these electronics. Small PMT. A small PMT was added in the center of the tank. Why? Some of the events were saturating, and with adding the small PMT, you can extend the range, and this also means you have more information near the shower core. So if you see the density of particles, it falls rapidly from the core, and so the more dynamic range you have, the more data near the shower core you can have. Then you have UMD, which are buried scintillators to detect muons. It's basically the same technology. This one, in fact, came first. But this one is buried at around 3 meters below ground. And this is an old picture. Now it's simpler with smaller, I think it's called manhole, but not sure. And for access to the electronics, but it's the same principle. You have bars of scintillators in here and bars of scintillators in there. The idea is the ground will block the muons and will block everything but the muons, and then you get a measurement of the muons. And this was the last one to enter, also in part because the European Union, someone got an ERC to do this, and the idea here is to install, I'm sorry, it's not visible with this resolution, so you install in here a radio antenna, and you collect the radio that the shower emits while it's developing in the atmosphere. So it's similar to a Cherenkov effect. It's radio propagated in the direction of the shower. And the great advantage of this is you compete with the fluorescence measurement, but since it's radio, it can work during the day. And so in fluorescence, we have like 10% of uptime, and in radio, it's expected to have a lot of uptime. So main idea, the SSD is more sensitive to the electromagnetic part, just because the electromagnetic part of the shower is more abundant, and so it will count particles, and most of the particles are electromagnetic. The tank is more sensitive to muons, because muons in the tank give more signal than electromagnetic parts that die in the top layer of the water. But there is no perfect separation. However, AugerPrime is also a multi-hybrid detector in some parts of it to detect everything. So you have radio, you have this low energy extension of the fluorescence, you have Amiga, which is buried scintillators, you have MARTA, which I will talk, which is to detect muons just in the water Cherenkov detector. You have Dayfield, which is a denser array to lower the energy, and then you have the SSD, which plans to extend good quality measurements up to the maximum energy. This one is applied to the whole array, and these are limited. The radio is also to the whole array, the other ones are limited. So, about MARTA. So, you have Amiga, or the UMD, which is detecting muons under the ground, which are not the same muons as in the tank. Firstly, because they are off to the side. Second, because they are buried, and you are killing some of the muons that are giving you signal in the tank. So we came up with MARTA. These are the founding paper of MARTA, and this is the founding paper of the MARTA acquisition system of the front end. And the baseline configuration was this. You have the tank, and you put 4 RPCs on the bottom, which have segmented readouts. So you start by solving the problem of how do we put RPCs under the tank, and it's simple, although it requires a lot of engineering. So you make precasts of reinforced concrete, and you have here a foot, and then you have here the slabs, and then you build a housing for the RPCs. Of course, you need to empty the tank, take the tank out, and then put the tank and fill it with new water. Then, what is these RPCs or these MARTA modules? So, they are RPCs developed at Coimbra specifically for this purpose. You can see here a picture of the active volume and its configuration. It has 2 gaps of 1 millimeter, and it's filled with gas, and then it's inside here. So this is inside this aluminum casing. Then you need power and control. You need the high voltage for the RPC, which is plus and minus 5000 volts. You need the gas subsystem to control and renew the gas. Inside the detector, you have here the output from the pickup electrodes, which are 64 coaxial cables. And then you have here the DAQ board, and the data interface is somewhere in here. Okay, the readout, and this is the segmentation of the readout. So this is the readout plane, and each of these paths is read individually. And so you get information on each of these paths, which is roughly 10 by 10 centimeters. I'm just giving you 10 by 10 so you can remember. In fact, it's 14 by 18. I have the number somewhere. Okay, so if it's a segmented detector, why? Why is it important? Because if the shower hits like this, in this corner, you will have a large contamination from electromagnetic that doesn't get attenuated. In here, you have to traverse all the tank, and so the electromagnetic is very attenuated in here. And this is the map of the traversed matter, and so you can select where you want to get your data. And so you can throw out things that have a low mass burden on it. So low attenuation, you have everything. Where you have high transverse mass, you have high attenuation, and this means you have muons. So the station, it's basically 4 modules. Sorry. But you need to transform these 4 modules into a functional station. And so it's not trivial because it needs to be autonomous, it needs to have low power, low communication, and it needs to interface to the existing tank, and it has to be in the Pampas environment. This means also it's 10,000 kilometers from Portugal, and it's 60 kilometers from Malargüe. The station, it's 4 RPC modules, so let's call this the module, controlled by a central unit, which is here, and you need to interface it to the water Cherenkov tank to get triggers and to get communications. You also need to have a slow control for this system, and you also need to consider you need to have some gas supply, even if small, with a small flow, you need to have this gas system for now. So prototypes. These were the 2 prototypes that we started with. In here, it was a prototype electronics, and the idea for the readout is basically you have the pickup electrode from the RPC, and in the front-end board, you basically amplify the signal and you get a threshold, you apply a threshold, and then this is digital signaling. Is the path active or not? Meaning there was a particle or there wasn't a particle, and this is the main acquisition scheme of MARTA, is to count how many paths were active along the time. And so with this information you get basically the number of muons. In this case you had a motherboard with several FPGAs, and this is the front-end board, which has very, very low noise. This is installed in one of our setups. You can see it takes a lot of space, and this is in Malargüe steel with the motherboard here and all the cables coming in. Okay, so in the field, this is still from the prototype. You just need to push it in place. Even I can do it. Someone said this. I won't say who it was. Okay, but there was a lot of power that needed to come to it, and in here there is a large station of solar panels. You just need to extend the cable from here to here, but you need to protect it, and then the staff was not available at this time to do the job. And so you see, by the way, this is Luis Mendes just looking. Okay, so we needed to evolve because it was not practical to do autonomous stations with this. And so we need to get power from a couple of solar panels, ideally one. And also the real estate is costly at the Pampa, meaning we have like 20 centimeters below the tank to put everything. I know it's 3.6 meters, but you want to instrument everything in this 3 by 3 square, and so it's complicated. So this required an integrated solution to minimize the power, meaning milliwatt per channel, and to minimize the data. So you can only transmit triggered paths. Let's say I had this triggered path at this time, and this was basically the maximum that the collaboration would allow us to transmit. Why? Because the array is constantly transmitting data from the low-level triggers to the central campus to make the computation give back higher-level triggers. And so if you mess with the communications, you can kill the array in an instant. And so the collaboration is very cautious about this. And so the chosen solution is basically an ASIC coupled to an FPGA, maintaining the same concept. So you have the path, you have amplifier and threshold, but this is now made in an ASIC with 64 channels, and then you connect this to one FPGA. And so the FPGA manages all the data, including the trigger and the seeking, meaning clocks and the triggers. This is the readout system, fully developed at LEAP, except obviously for the FPGA and for the ASIC. You have here the inputs. This is the first version with the connectors, and then you think about the cost of these. You multiply the cost of each connector by 64 and by the number of so on, and then you end up soldering the cables in these boards. No problem. Why? There are two connectors here, so this gets attached to the RPC, and this one can be changed easily. So you have the inputs, they come directly to the Maroc, then the outputs come to the FPGA, then you have an USB port for testing mainly, and you have an LVDS interface to talk to, in this case, to a central unit that controls everything. A first field station is the Peter Mazur tank, so here just with the precast, just with the structure, and it already has the SSD in here. It's a fully upgraded station. It has the SSD, it also has the Amiga one, and we are in the infill area, meaning that we can have more data or more showers. They are low energy, but we can have more showers for testing and so on. Okay, this is the configuration. You have solar panels. You have what we call the MARTA box, where we put our central unit. You have the RPCs where the front-end electronics are inside. You have the electronics of the tank, and then we had to add some batteries. And outside you have the gas roll where a small bottle of gas is installed. Oops, sorry. Your battery is running low. If it dies, it's a disgrace. Okay. Hopefully it's going. Yeah. So, slow control and monitoring. This is just to tell you that these are developments that we are not sure how they will work on the Pampas, and so this is a new development. And you have all these sensors. These are these are central sensors, let's say, and this one is per module, and then you multiply this by 4, and you can see you have recording the voltage, the current, and then you have humidity and temperature. Mainly, these are the main parameters that get stored, and also the pressure, the atmospheric pressure on site. Then this is all LIP. This is an interface done by José Carlos using the Grafana. We followed the same approach that Auger does, which is we record the data, we throw them to a database, we replicate at Lisbon, and then we have the interface. Data is stored in a database, but we have this nice interface to have a quick look at it, some dashboards. The central unit is something that stays in here. So you have, we show a CPU plus an FPGA, meaning it's a SOC FPGA. And we used a development kit. So this part is bought or from Terazik, I believe. And we developed this part to have slow control interfaces, and in here you have LVDS interfaces, so fast interfaces to the modules. So you can see here all the yellow cables are transporting data to and from the modules, which are somewhere in here. Of course, one of the things that you can try, and then you notice that really long cables need some more care. And the other thing is that there are lots of static in this field, because there is lots of humidity, and you need to protect these lines, otherwise you can burn the input-output. So in the field, not having a socket, it's not so easy, and the power system comes from solar panels that have regulators, and they tell you it's 24 volts. It's not. It's like 20 or 26, or it fluctuates. So we developed this nice power supply unit that has an input from 18 to 28, so you can put anything that you want there, and then it falls to low voltages, and then to make it stable, you make LDO, so a low dropout in the end. And so mainly these are very efficient, and you only spend a little bit of linear drop down to pass like from 6.1 to 5.5 or to 6. So this is the power supply unit with the added benefit that you can disconnect all the things, because you cannot go there to, well, you can, but it's 60 kilometers. And so you mainly need to have, what we found out also is you need to have one line that never gets cut, so you can control the rest of the tank. And so you can disconnect everything, but one of these parts needs to be alive always, so you can reboot the system. And so you can connect and disconnect. So you might think electronics is a dull thing, but you can see Ricardo is very happy with the DAQ. It was his PhD thesis. So other lessons from the field. So you have this wildlife, where you just open the gas bottle, you take out the bottle, and then you find all of these, which are just some small animals, doesn't care. These are very preoccupant, because they are venomous, and they can kill. Ruben, how many minutes until you die? It was like 3 or... Yeah, so if you get hit by this one, you need to be very careful here. And the thing that you think, oh, I will just adjust this and recompile, means sitting on the ground with the laptop, and you need to find, because it's very aggressive, the sun there, and so you need to find a place to make bug corrections, means this. And of course, if you go to the field during lunch hour, the staff will prepare you this. I don't recommend a lot. And then you see this part, you need to get a truck to go there. It's not always available. And then you need the weather to collaborate. And so you can see that to pass the cables, you need to pass some tubes to communicate between the different parts. And it's not ideal conditions to work and to develop stuff there. You might need to wait for good weather, or you can go and the weather can turn to something like this, where you can see it, heavy rain at far. And so everything takes really a long time. And if you forget to connect the cable or so, it means that it's like 2 hours just to get there. The staff can help, but they are not experts. So if you need to change like one cable or so, it might happen that they won't be able to do it. Well, I say some, but many problems only appear when you are commissioning. So you test it in the lab, everything is working, and then you get there, and something is a bit off. And you can only test really the interfaces on the field. Also, the materials deteriorate. Just as an example, last time we had at a certain point to change all the gas tubing, and then we found that some of the tubes were brittle and some were dented in some parts, and then it's a small leak that you don't see it, but then it's enough to degrade the performance of your detector. And so of course, to change this, it implies a lot of effort and luck. So let me talk you about a spin-off. So the muonodoscope for the characterization of the tank. So the collaboration at a certain point had old data, like a scintillator on top and a scintillator on the bottom of the tank, and it only had this to extract 1 parameter for the calibration of the tank. What have we done? We installed an RPC on top and 1 RPC on the bottom of the tank. Fortunately, this is more accessible. This is in the central campus. And the idea is that you define muon tracks, and then you get the response of the tank. And this is the results that are from the first acquisition that we made years ago. And so you want to understand the response of a VEM. VEM is defined as a vertical centered muon going from top to bottom. And you can see here the results agree with simulations under the to the percent level. The other thing that was not done, so this was basically a repetition, the other thing that was not done was the evolution of the response of the tank with the angle. And at a certain point, people were thinking about 10 to 15% of uncertainty in this study, or in this measure, or in this variable that then gets propagated in the results and kills you some results that depend on this. We measure it, and you can see the agreement with simulation is very nice. It's under 2% fluctuations, and so this gives you credibility and allows you to expand simulations measurements that depend on the angle of the showers. So this is just a picture from the installation, and we have done recently an upgrade, and we needed to change the top RPC. It died after 10 years with daily excursions of 20 to 30 degrees. And so when the sun rises, you can have like 20 something degrees. When the sun falls, sets down, you can have like 1 degree or so. We have the new it's a production model of MARTA. We installed the new electronics. We deployed the central unit for the triggering. It's the same solution being used in the field. And we also asked, and the collaboration also had interest in this, to use the upgraded electronics and installed also an SSD. And we can collect with this setup in 1 day the data equivalent to months in the previous setup. And so this is a new tool for the collaboration. This is the setup, top RPC and bottom RPC. Unfortunately, the SSD is here, the standard position, and we cannot move the bottom one to this side with small efforts. So we can see, yeah, this kills the resolution. So we can see here events and events with the SSD, with the new detector in here. And this region of 1.2 meters track length is basically vertical muons going through the SSD, which is this region in here. And, well, you cannot see it, but hopefully in Zoom they can see it. You can see the distribution of the signal in the SSD, but I cannot show you this. Okay? And so it's also preliminary, so you don't miss a lot. Okay, exploring data and capabilities that we have already from the Peter Mazur tank. So it's been commissioning to, I would say, taking data around November. But we did something different in this station. In these two RPCs, we overlapped them. And so this region is seen by the two RPCs at the same time. So we lost a bit of area in here and in here, but we gained the possibility to measure the efficiency. So we measure the efficiency basically by saying it had to pass on the tank, so we can get rid of the noise. It had to pass on one RPC, and what's the signal on the other one? The RPCs are segmented, so here you have 1 to 8 and 57 to 64 pods, and the other one is 1 to 8 and 57 to 64. So this is the top view of them, and now you start combining RPCs. And if you make the sum of the pods that are coincident, so this one is coincident with this one, and then you sum up 67. It's the same for the pod in the side, and then you also sum 67, and it's the same for the pod on the top, the 12 and the 55, and then you also sum 67. And so coincident pods always sum 67, and that would be the ideal world, let's say, if everything was working well. But if you shift the RPCs, if you shift it horizontal, then you are combining the 11 with the 48, and then you sum up 59. And if you make a vertical shift, then you sum up the 11 with the 55, and you get 66. Okay? Let me just tell you that this method is not mine. It's from Guilherme, who is doing the integrating project with us, and we also got very suspicious in the beginning. And it's the same if you select other pairs of it, meaning you have this, let's say, the count of events, and you sum the pods, and the okay one is the 67, and so you get this high peak. Then if you have a horizontal shift, you have these peaks in here, and if you have a vertical shift, you have this one, and obviously this one and this one, it's a horizontal shift and a vertical shift. Okay, now you can start simulating and shifting your RPCs and understanding how to make this kind of graph, because ideally you should have only one peak, and now you can shift it. You can say, okay, the amount of here and the amount of here, the relative ratio will give you the amount of shift. Yes, more or less, because they are a bit far away, the showers are not vertical, they have, and so you make a simulation, and, well, you make a lot of simulations, you calculate the chi-square, and you try to find the minimum, which is somewhere in here, and it suggests a shift of about 3 to 4 centimeters in width. And I'm just referring this one because I have troubles believing this. The other one, we know that we shifted 2 pods and that it's not very well aligned. This we know for sure. This one, at least I was thinking it was more aligned. And so that's, but okay, 3 to 4 centimeters, it's a reasonable shift. And so then if you do the 2D module, which is, they are on top of each other exactly, and everything is vertical basically, you get this. And if you consider the showers that are inclined and that the RPCs are a bit separated, then you get this module is the blue, it's the yellow compared to the blue in here. And you can see they are very nice describing that. So that's a way to measure the shifting, the disalignment of these RPCs, and why to get the efficiency of the RPCs themselves, we need to get rid of this. And the preliminary results are these ones. So this is the path efficiency for RPC3. So these ones are 0 because they are not overlapped, and for the other one. And you can see this lack of efficiency here. It's probably due to the shifting of the RPCs. Then we can compute the average efficiency, and we are around 75 or so for the 2 RPCs. So this is still preliminary. Next steps, we want to look at the evolution of the RPCs efficiency and start correlating with the parameters that we have, the temperature, the pressure, and the high voltage or the reduced electric field. But okay, we need to get more data and to explore this. At a certain point, this was shut down because we are still operating with a high flow of gas to be sure of the performance of the RPCs, and so we can operate for like 1 month or so, and then the bottle needs to be changed. And again, the staff could go there, but last time some of the problems might be introduced by staff changing the bottle, so need to be careful at this phase. So what can we do with a single station? So we have one station in there. I know it's not standard, but it's an upgraded station from the other ones because it can measure directly the muons on the station. And so you can compare with the other detectors measuring the same thing. So this is the work by Milton Freitas. He's now starting the PhD, so this is basically the master thesis and beyond. So Ruben has a strong case to measure the particle energy spectrum, namely the muon spectrum or the electromagnetic spectrum of energies. And so the question is, can we measure it? So we started doing this question, and we have here the simulation, and we have here the distribution of the energies or the spectrum of energy, and we have 3 detectors. The SSD, it's a particle counter basically here on top, so it counts everything. The Water-Cherenkov signal, it's proportional to the muons, it's the track length, and so you know how to calculate it. And the electromagnetic, it's basically proportional to the particle energy because it will interact and make a shower, and the number of particles in the shower is proportional to the energy. The RPC is also a counter, a segmented counter on the bottom, and you can get 2 informations from it. You can count the muons if it's a high overburden, and you can count everything if it's a low overburden. And we are still exploring the muon count at some point. Modifying the particle energy distribution, so you can see there 2 lines, and the red one and the red one is the modified one, and the original is the black one. Sorry, it's not completely visible here. And you have the ratio here. The idea is that you don't change the spectra up to a certain point, and then you change it. And you put this in the simulation, you simulate the detector, and you see what you get. So the modified one is this one, and the original is this one. It doesn't seem to say too much, but when you make the difference, you can see the blue ones is a deficit and the reddish ones are a surplus. And so you are migrating events from here to there. This one is the Water-Cherenkov signal in terms of compared to the SSD signal. Since we have different responses, we expect the plots to evolve differently. In this case, you have, here we are testing the electromagnetic component, and we are looking at the signal in the Water-Cherenkov detector with the SSD. And here we are looking at the RPC hits versus the signal on the tank. So what do you expect? The SSD should not change too much the number of particles count, because you are just changing you are not changing the number of particles, you are basically changing the energy of the particles. But the WCD should change, and that's basically what you see. You see it's shifting up. On the other hand, the RPC is below the tank, and so particles with more energy penetrate more. And so if you have more signal in the Water-Cherenkov tank, you should have more RPC hits, and then it goes in this direction. So the other thing that Milton has done is that he tried to do a difference, to do different kinks in the spectre. So 1.5 and 6, and this defines the magnitude of the change that you do. And then you have here for 1.5, 2, 3, 4, 5, and 6. And you can see it developing and being more pronounced, the shift. Then at a certain point, you might question, yeah, how can I measure this shift, or how can I quantify this? And then you need to find some strategy or some variable to do this, and it's like the positive barycenter and the negative barycenter, and you are looking on the shift and on the direction. And now you can do simulations and see what is happening with different ones. And then you have here the WCD versus the RPC, and the SSD versus the WCD. So tank RPC and scintillator and tank. And you can see the evolution, and the nice thing is that they align in the same direction, let's say, and they grow with the amount of the change that you do it, meaning that it might be possible to measure it, okay? And so you might be able to get to the data and check it against simulation and see what is the kink that I need to give it in the simulation to have a better description of my data. Sorry, it went back. Okay. So this is the method to, with just one station, start measuring this. And there is a paper in preparation, measurement of the shower components energy spectrum using a hybrid detector station. And this is a short author-list paper, meaning it's not from the collaboration. And so the main complication here is to develop tools for a simulation outside of the collaboration. So reaching the conclusions. So the Auger data from phase 1 raised new puzzling questions or new measurements to be made, and we are doing a great effort to increase the data quality and address systematic uncertainties. I didn't refer this, it's not only a question of statistics, it's not waiting more, it's not upgrading the detector and wait for long statistics. Part of it is understanding our detector to train machine learning algorithms to go back and recover our data from phase 1. And so we expect to have the full data set saying things with more power to this. We want to disentangle primary variations, meaning mass composition from shower development on the atmosphere, and the MARTA allows to have direct information from muons crossing the tanks, and of course with a limited number of stations. Even with only one station, we can give important contributions. So plans, we want to, of course, operate, test, and explore the Peter Mazur tank data. This is our test tank, let's say, our production test tank. We have the idea to make a hodoscope in this tank. So we have 4 RPCs on the bottom, and if we could have RPCs on the top, we could have data from showers, not atmospheric muons or atmospheric particles, telling us the direction of the particles. This requires a lot of engineering. We are doing responses on the Water-Cherenkov and the scintillator response to particles, and about the engineering array. Now we have, let's say, one station, and the next step would be either a twin station nearby without the measurement of efficiency, so the standard station nearby, to behave more or less like a twin. So to have 2 stations, 2 MARTA stations on the same event. And to deploy other stations, we would consider deploying it on the larger array to maximize the events with higher energy. In here, there is a strategy that we might follow, which is we want events with at least one station. We don't require, in principle, to have lots of stations, lots of points on the density of each shower. We want more showers, and this would go to a strategy of one station with MARTA here and one station far. And so when a shower hits here, it's triggered by the standard array, and you get the MARTA data. If it goes in here, and so the area of influence of one MARTA station could be bigger. Okay, and that's still to be discussed. Perhaps the 2 options are viable. And so let me just thank you.